Hello everyone, welcome to this video. This is going to be a walkthrough of a problem in kinematics called the airplane flight plan problem. And essentially what we have here is an airplane that is going to take a flight that involves going through 5 different displacement segments. And these are actually going to be 5 different displacement vectors. As you know, a displacement vector is a mathematical object with a magnitude and a direction. And a displacement vector is a vector that tells you how far an object has traveled from one point in a straight line to the second point. So we can start drawing out our displacement vectors. Here's going to be the first one, v1. We're going to have another one here that's going to be at a 30-degree angle. And this is not going to be drawn to scale, everyone. This is just to get an indication of what's happening. We're going to have another displacement vector here, v3, going horizontally. Next, we'll have a fourth displacement vector, v4, that will again be at a 30-degree angle to the original path. And then finally, we're going to have a displacement vector, v5, that's going to go all the way across here to the second quadrant. So our plane is making this zigzag path and then returning back west. And our goal is to figure out 3 things. One thing is we would like to know what is the magnitude of this displacement vector. That is the total displacement vector, or sometimes called the resultant vector. I would also like to know the angle that this vector has, and that's going to be basically this angle here, coming from the positive x-axis up to that. I'll call that theta r. And I'm also going to want to know what is the total distance traveled, which will actually be the sum of all these little segments on the way of the flight. So let's begin by defining some numerical values for all of our displacement vector magnitudes. So this is going to be, we're going to write these vectors in a notation, in a vector notation, that's going to have magnitude, comma, and then a direction, which is going to be an angle. And this is going to be, these angles are going to use a convention that all the angles will be measured from this positive x-axis direction, taking counterclockwise as positive, and only using positive angles. So we have those constraints so that we have unique values of angle here. Okay, and so now we can define all of these vectors. We have v1. That is going to be a magnitude of 25 miles at an angle of 0. And now v2 is going to be given to us as having 20 miles along that 30-degree angle path. v3 is another horizontal. That's going to be 150 miles in the 0-degree direction. Then we're going to have vector 4. This is again inclined. This is going to be 10 miles in the 30-degree angle direction. And finally, we're going to have vector 5, whose magnitude is 262 miles, and the angle is 180 degrees, so all the way to the negative x direction. Okay. So those are our magnitude direction notation for the 5 vectors. But in order to find out this resultant vector, we need to actually add these vectors together. So that's one of the things you can do with vectors. They're not regular numbers. They're these mathematical quantities that have a magnitude and a direction. And in order to add them, what you emphatically can't do is just add all of these magnitudes, because they're not just, scalar numbers. So the trick here, guys, is in order to add these vectors together, we have to first find the x and y components of each vector. So let me show you what I mean by that. v1 has an x component. It has a projection to the x-axis that is actually just equal to the magnitude of the vector. So I can come over here and start writing my x component, y component, notation. And so for v1, it's really easy. You could just write it directly. I'm going to have 25 miles, comma, 0 miles. So I have an x component of 25 and a y component of 0. So that was pretty straightforward. Now for v2, I have to do a little bit more work. I have to recognize that there is going to be a projection of v2 onto the x-axis, which will be this dashed vector, and then there will be a projection onto the y-axis, which will be this one. So I can actually write this as v2x and v2y. And as you can see, they make up sides of a right triangle. So this is where trigonometry comes in. To find these missing sides of the triangle, given the hypotenuse, which is actually the magnitude, and given this one angle, we can apply trigonometry to find these. So I'm going to go to make an aside here. I'm going to pull this page from your view. I'm going to bring in another page. And so here what we have is just a zoomed in view of that vector number 2, where we have the actual vector 2, we have its x component, its y component, and this angle. And so this is where we can apply the rules of SOHCAHTOA. I'm just going to say it aloud. So for cosine, we need to have the adjacent side over the hypotenuse side. So if this is our angle, the adjacent side is v2x, the hypotenuse is v2. So here you can see we have adjacent over hypotenuse is equal to the cosine of the angle. And this is in some ways the definition of the cosine for this right triangle. We can then multiply both sides of it by v2, and then we will have here that v2x is equal to v2 times cosine of theta. So we're just writing down that the trig function is a ratio of sides, getting that ratio of sides correct, and then multiplying both sides by the denominator to solve for that x component, which was one of these unknown side lengths before. You can do something very similar with the sine, get the side length ratio, multiply both sides of this expression by that hypotenuse length, and then that hypotenuse times the sine of the angle. This little Greek letter theta is of course just the angle. That will actually give us the other unknown side of the triangle, which we're labeling here as v2y. So with these two expressions, so hypotenuse times cos or hypotenuse times sine, those are going to give us the x and y components. I'll just mention here, we're going to need this later, that you can also define the tangent function as the ratio of the y part over the x part. And then we'll do something with that later to solve for this angle. So with these definitions in hand, let's go back to our main problem, which is here. And we were trying to figure out what is the v2x and the v2y for this triangle here. So what we can do is say that v2 is equal to its x component, which will be a hypotenuse of 20 miles times the cosine of 30 degrees. So there's my x component. I can still type this into my calculator and get an exact value, and that will end up being 17.32 miles as my x component. And now I still need the y component, so using the formula we derived earlier, 20 miles times the sine of 30 degrees will be the expression, and that comes out to 10.0 miles. So I now have my expression for v2 in x component and y component notation. Well, we move on to vector 3, and this is another horizontal one, so we can just write the components without any trig. We're just going to have 150 miles as the x component and 0 miles as the y component. But back to vector 4, this is another one that has an x and y part to it because it's at an incline. So here's v4x and v4y. v4x is going to be the magnitude of v4, which is 10 miles, times cosine of 30 degrees for the x component, and 10 miles times sine of 30 degrees for the y component. So I have already plugged those into my calculator, and the values are 8.66 miles for the x component and 5 miles for the y component. Okay, last one we need is vector 5. Now this one is horizontal, but we must respect the fact that it's pointing in the westward direction. And so the way that that will work is we're going to have negative 262 miles as the x component, and then 0 miles as the y component. So remember, vectors always have to consider the direction that it's headed, and that's why we put this negative sign over here. Okay, so just to remind you that what we're trying to do right now is add together all these vectors. And in order to do that, we needed to first write them in this x and y component notation, because the answer that we're looking for here is going to be this VR, this resultant vector, and that too has an x and y component. So I could have a VRX and I could have a VRY. And this is a 90-degree angle, and this angle here will be some theta. And so the beauty of this is by adding together basically this column, all of these x values, I will get the VRX, the sum of all the x. And by adding together all the y values, I'll get the VRY, which is the sum of all the y. So let's create a new section here for our resultant vector. Resultant vector. And so we're going to have VRX equal to the sum of all those x components. So just to be explicit, let's write it out. Here's the 25 miles. We need to add to it the 17.32 miles. We need to add to that 150 miles. Continue adding now 8.66 miles. And then finally, actually subtract a negative add a negative 262 or subtract 262 miles. So those were all of these x components put together, and that comes out to negative 61.02 miles. Okay, so that basically is the length of this vector right here. We just found this VRX basically by taking this distance, this distance, this distance, this distance. Oh, and sorry, that was off view. So taking this V1, V2x, V3, V4x, and V5x, that is how we just got this VRX value. And it's negative, as it should be, because it's going from the origin in the westward direction. Okay, so now we want to do VRY. That's going to be the sum of all these y components. So 0 miles plus 10 miles plus another 0, plus a 5, and plus another 0. And that, of course, will just be 10 plus 5 is 15 miles. And that, in our diagram, corresponds to this vertical VRY, which is just this V2y and this V4y. Okay, so now that we have our VRX and our VRY, we need to find the total magnitude of VR, which is going to be, of course, this hypotenuse, and we can just invoke here Pythagoras' theorem. So anytime you have a right triangle, here's our little right angle, and you have two short sides and you have the hypotenuse, it turns out that the short side, let's say call this side A, this side B, and this side C, I can even put a little reminder there, that A squared plus B squared is equal to C squared. So using the notation of this problem, we're going to have VR, and here's my notation for the magnitude of VR. The magnitude of VR, it'll just be equal to VRX squared plus VRY squared. And taking the square root of that expression, we will get, let's put in the actual numbers here, 61.02 miles squared, and here's the 15 miles squared. And so that expression will come out to be 62.84 miles. So we've solved for the first thing that we needed in this problem, which was the actual net displacement magnitude that the plane has gone from its starting point here to the ending point. We now have its displacement magnitude. What we'd now like is the direction of that vector. And so what we need to do is find this angle theta inside our little right triangle. So just to remind you again, before we had this triangle, and I reminded you that the y part over the x part, this was for the v2 vector, but the same idea works for any triangle. The y part over the x part, or this opposite side over the adjacent side, will be equal to the tangent of the angle. So we're going to apply that reasoning over here. VRY over VRX should be equal to the tangent of this angle theta. Let's write that down. VRY divided by VRX should be equal to the tangent of theta. And let's do the inverse tangent function of both sides. The VRY is going to be 15 miles. The VRX is going to be 61.02. I'm using the positive value because for me this is just the side length of a triangle. It's not necessarily a displacement component, and that will be equal to theta. So if you put that in your calculator, you will find a value of 13.81 degrees will be this theta. But remember, we're not done because that was only the theta in this triangle, but the problem is asking for us to get the angle in the sine convention, going from positive x-axis counterclockwise to the vector. So we need the theta r. And that can be found easily. All we have to do is just take theta r is going to be equal to 180 degrees minus theta. So theta r will be 180 degrees minus the 13.81 degrees, and so theta r is now just 166.19. I'm not worrying about significant figures in this problem, guys. I just want to give you enough digits so you can easily confirm that you're typing the same thing that I am here. So I'm not doing any sig fig rounding. And let's just consider one last thing. We've now found the displacement vector and its magnitude. The last thing we wanted was the distance, the sum total distance that has been covered as the plane flew through these 5 segments. And so for that distance, we're actually just going to add up all of the original displacement magnitudes as though they were just numbers. So when I said that we couldn't do that before, I meant that you couldn't do that if you wanted to get the net displacement. But it turns out that if you do just add those, then you will just have the total distance traveled. And of course, we're assuming that the plane makes these super sharp, like abrupt turns, and that there's no like little turn radius on each one of those. So that's just like a little assumption that we're making here. But you get the idea. If we just add up all of those little path segments, we'll have a total distance of 467 miles. Whereas the displacement, which just takes you from the starting point to the ending point, is only 62 miles. So in this case, because the shape of the path is basically a big loop, we can see that the distance covered is going to be way bigger than the displacement. The distance and the displacement would only be the same if the object had just gone in a straight line from the start point to the end point. So there you have it, guys. This is the kinematics airplane flight problem. We've reviewed vector addition and the trigonometric procedure of finding x and y components of vectors and then adding them. And then we've discussed the difference between distance and displacement. Hope you enjoyed the video, and I will see you on the next one. Thank you.